Thanks everyone for coming. So today we have Lenny Fukshansky from Claremont McKenna College, and he'll be speaking about lattices from group frames and vertex transitive graphs. So you can take it away whenever you're ready.
Right. Thank you very much, Michelle. So first of all, I want to thank the organizers for having me. And indeed, I'll tell you about lattices from group frames and vertex transitive graphs today. So this is joint work with Diana Nidell, Josiah Park, and Jesse Shin. This was actually done pre-pandemic, so I was able to see my co-authors in person. Okay, so let me see. Okay, so let me start with some frames notation. So what's a frame? So a spanning set for a k-dimensional Euclidean space consisting of n vectors where n is usually greater than k is called a tight frame. If there exists such a real constant, gamma, that for every vector x in my space, r to the k, the squared norm, so I write double bar for Euclidean norm throughout the talk, the squared norm of this vector can be computed as gamma times this sum of squares of inner products with the frame vectors. So this is just the usual dot product. Okay. So let's see. Now we will say that a tight frame is rational if if essentially all of the dot products between the frame vectors are just rational up to some scalar multiplication by the same real number. They can all be made rational by the same alpha. Okay, so there is a notion of group frames. So if G is a finite subgroup of the group of orthogonal k by k real matrices, then G acts on the space Rk by left multiplication. So we say that this action is irreducible if the only invariant subspaces are zero in itself. So only, and the full space, I mean. So if there are no non-trivial invariant subspaces. So it turns out that irreducible group action leads to nice tight frames. So what you can do is take a non-zero vector f and then take its orbit under the action of this group. Such a collection is called a group frame, or G frame, sometimes people say. So in case the action of G is irreducible, then we say this is an irreducible group frame, and it is a known fact that irreducible group frames are always tight. Okay, what I want to do is.
I'm sorry, Lenny. Can I ask a quick question? Is it easy to see that the irreducible group frames are necessarily tight?
It's not super difficult, but it's a lemma. I mean, okay. I'd have to think about it for a few minutes.
All right, never mind. Yeah,
okay. But I can tell you. You know, there's the book by the New Zealand guy, the book on tight frames, Introduction to Tight Frames.
Oh yeah, okay. Mm-hmm.
It's in there.
Waldron. Okay,
yeah, Waldron. That's it. Yeah.
Okay.
Mm-hmm.
Okay. All right. Thank you. Yep.
No,
sorry.
Okay. Sorry. Yeah. Oops. All right. Yeah. Where I'm going with this is I am mostly interested in lattices, so I want to start with frames and see if I can generate a lattice by them. So in other words, given a frame F, so nk frame, right, meaning that n vectors in k-dimensional space, let me write L of F for the span of F over the integers, right? So the set of all linear combinations with integer coefficients. So then the question I want to ask is, when is this a lattice? So meaning a discrete subgroup of R to the K. Well, clearly it's a subgroup under addition. The question is it discrete? And in general, if I take some, so you see, if I had K linearly independent vectors, then yes, it would necessarily be discrete. However, if my collection of vectors is overdetermined, then one can come up with examples that where a set like this is dense. So the question is, when is it discrete? Well, so here's a theorem which is actually not hard to prove. We prove it in more than one way, that such a set is actually a full rank lattice. So in case my F is a tight frame, then this set is a full rank lattice, if and only if the frame is rational. So after we proved it, we actually discovered that a similar result was proved even slightly earlier by Sunada. His proof is quite different from ours. In particular, ours is a lot shorter. Yeah. Okay, so well, then the next natural question is, well, what kind of lattices can we get in this manner? And well,
Lenny, can I interrupt just a minute, please?
Yes.
You might have already defined this. What's a rational frame?
So let me just go back here. So rational means that the scalar products of the frame vectors are rational up to the same scalar multiple.
Okay, thank you.
No, my pleasure. Okay. Yeah, so the question I'm asking is, what kind of lattices can we get this way? And of course, I'm going to answer it with a question. What kind of lattices do we want to get? All right, so well, let me tell you a little bit about lattices and the special types of lattices that are particularly nice for this and that or that purpose. And then I'll tell you what kind of lattices we want to get. So let me start by defining the minimal norm of a lattice. So remember, a lattice is discrete, so I can define the minimal of the Euclidean norm of all non-zero vectors. So this is well defined. So the set of minimal vectors of L is the set of all vectors that have this minimal norm. So from here on, I will write, so S of L will always stand for the set of minimal vectors. And let me just list them as x1 through xn. So the cardinality n must always be even, right? Because, well, if x is a minimal vector in L, then so is minus x. So they always come in pairs. Okay, so in principle, the cardinality of the set of minimal vectors can be smaller or equal to or larger than twice the rank. So right, perhaps the easiest example is the integer lattice z to the k. So the minimal vectors there are just plus minus the standard basis vectors. Okay, so we say that the lattice is well-rounded, abbreviated WR, if the span of the so if the space that is spanned by the minimal vectors is the full space spanned by the lattice. So for instance, the lattice z to the k, that's a well-rounded lattice. But you see, so in order for the lattice to be well-rounded, you need, so your set of minimal vectors needs to have a full collection of linearly independent vectors. So it needs to be a basis for the space, not necessarily for the lattice, but for the space. Okay, so a very important class of lattices are the so-called eutactic lattices. The name comes from eutactic point configurations on spheres. I guess eutactic translates from the Greek as well distributed or well positioned. Yeah. Well, a collection of vectors, say x1 through xn, is called eutactic if there exist the real numbers c1 through cn called eutaxy coefficients, so that for any vector v in the space, the norm squared can be expressed like this. So if the set of minimal vectors of my lattice is a eutactic set, then the lattice is called eutactic. Now, in some very special cases, I can actually take all of these eutaxy coefficients to be equal to each other. So in this case, we say that L is strongly eutactic. So notice, of course, that if I take all the coefficients equal to each other, then this is just the tight frame condition. Okay. All right. So there is another unrelated important condition on lattices called perfection. So a lattice is called perfect if do this. Take a minimal vector, write it as a column vector, and then multiply it by its transpose. Right? So column vector multiplied by the row vector, I get a k by k matrix. It's a symmetric matrix. So I can then take the set of all such symmetric matrices that come from this minimal vectors of my lattice. And the lattice is called perfect if this collection spans the space of all k by k symmetric matrices as a real vector space. Okay, so notice that this, so both the eutaxy and the perfection condition at the very least require my set of minimal vectors to be sufficiently large. Well, in fact, not just sufficiently large, but also to contain many enough linearly independent vectors. So in fact, it is a theorem that both eutactic and perfect lattices have to be well-rounded. Okay, but now I should say that eutaxy and perfection are independent conditions. So there are eutactic lattices that are not perfect, and there are perfect lattices that are not eutactic. An important point is that, so there is a certain equivalence relation, natural equivalence relation in lattices called similarity. So two lattices are similar if you can get from one to the other by orthogonal transformation and dilation. So up to the similarity, in each dimension, there are only finitely many eutactic and finitely many perfect lattices. So there are infinitely many well-rounded, but only finitely many eutactic and perfect. Okay. So I actually say it here, you see. All right. So good. Let me also define, so perhaps the most classical and the most famous problem on lattices is the sphere packing problem, right? So what I can do is I can associate a sphere packing to a lattice. Well, I can do it as follows. So for instance, at each point of the lattice, take a very small ball so that none of the balls overlap, and then start expanding all of these balls simultaneously until they touch and stop. So this way, we have...
Can I ask another question? I'm sorry.
Yes.
In the definition of lattice, do you always assume that you're starting from a tight frame?
Oh, no, no, no. No, a lattice is just a free Z module. That's all it is.
Okay, but in the definition that you gave of a lattice, Was it just like to illustrate something? Because
oh, yes. So what I'm trying to say here, hold on. Yeah. So here, specifically for a tight frame, I define the set L of F, which may or may not be a lattice.
Okay.
Right. So, and then this theorem that we have says that in fact it is a lattice, if and only if this tight frame is rational.
Okay.
Right. But a lattice in general,
Okay.
yeah, just a free Z module. Yeah.
Okay. Thank you.
No, my pleasure. Yeah. Okay. Right. So so you have a sphere pattern associated to a lattice, and so the classical problem in discrete geometry, which goes back to, well, probably at least 16th century or so, is what is the densest sphere pattern in a given Euclidean space? Well, back in 16th century, they were thinking specifically of the three-dimensional space, but you can formulate this question in any Euclidean space. Now, the sphere patterns associated to some lattice are a special class of sphere patterns. Not every sphere pattern comes from a lattice, but those that do are specifically very nice. Well, in some sense, because they're easier to study. So the pattern density in general is the proportion of the space covered by your spheres. So pattern density of a lattice can be computed by this formula. So it's let me tell you what is what here. Here's one way to think of a lattice pattern. So there is around every point of a lattice, you can define a certain polytope called the Voronoi cell of a lattice, and then this Voronoi cells tile the space. So what you can do is the volume of one Voronoi cell is the determinant of the lattice, which is just determinant, absolute value of the determinant of its basis matrix. The way to construct a lattice pattern is by essentially inscribing a sphere into each Voronoi cell. Now, the radius of such a sphere will be the minimal norm of the lattice divided by 2. So that's so essentially what you see here, this omega sub k, this is just the dimensional constant, which is the volume of the unit ball in RK. So then this divided by 2 to the k is the volume of a ball inscribed into the Voronoi cell divided by the volume of the Voronoi cell. So that's proportion of the space covered by one ball inside of the Voronoi cell, and that's the density of the pattern. Okay. Now, space of full rank lattices can actually be identified with, you can think of the space of you can think of the GLK of R under the action of GLK of Z by what? Right multiplication, which is just change of basis, because multiplying by any matrix from GLK of Z just takes me from one basis of a lattice to another basis of the same lattice. So then this kind of quotient space is the space of full rank lattices, and delta, the pattern density, is a continuous function on the space. So therefore, we can talk about its local maximum. So if a lattice is a local maximum of this pattern density function, it's called extremal. So there's a very famous theorem of Voronoi from 1908 that says that a lattice is extremal if and only if it is perfect and eutactic, right? So that's the significance of this conditions, perfection, eutaxy. Okay. This theorem of Voronoi, and actually there are many additional results later on. So perhaps I should mention there's I don't have it in my slides, but there is also a very nice theorem of Avner-Ash, much more recent than Voronoi, but 1970s, which says that a eutactic lattice is actually a so any eutactic lattice is a critical point of the Pekin density function. So if the lattice is eutactic but not perfect, it's not local maximum, but it's still a critical point of the Pekin density. Okay, so so these observations kind of emphasize the importance of eutactic and especially strongly eutactic lattices, because those turn out to come up especially often in the study of Pekin density and related problems. Okay, so as I mentioned before, right, this strong eutaxy condition is essentially the tight frame condition. So one can think of it this way: a lattice L is strongly eutactic if and only if its set of minimal vectors forms a tight frame. Okay, so and then we have this theorem, which is about irreducible group frames. So suppose that G is some group of K by K real orthogonal matrices. F is a vector. Yeah, so perhaps I should say finite group. Yeah. So then define the frame to be just the orbit of the vector F under the action of the group G by left multiplication. So if this group frame is irreducible, is rational, irreducible group frame, then the lattice is strongly eutactic, right? So I need the frame to be rational in order for L of F to be a lattice, and then if it is irreducible, this lattice turns out to be strongly eutactic. Okay. Well, so then one can ask, so great, but how can we construct rational irreducible group frames? So one source of such objects comes from transitive graphs. So let me tell you a little bit about graphs. So suppose gamma is a graph on, say, vertices V1 through Vn. So it's called vertex transitive if the automorphism group of the graph acts transitively on the set of vertices, right? So I can get from any vertex to any other. Now, there is a stronger notion of distance transitivity. So the distance between two vertices is just the number of edges I need to travel, the minimal number of edges I need to travel to get from one vertex to the other. So suppose my graph is connected, then it's called distance transitive. If so, if I pick any two pairs of vertices, say ij and kl, at the same distance from each other, then I can. So there exists an automorphism that takes I to k and j to l, right? So essentially, so paths of the same length can always be taken to each other by an automorphism. Okay, so distance transitive is necessarily vertex transitive, but it's a much stronger condition. So even vertex transitive is a pretty special condition, but well, luckily, as I will show you, there are plenty of examples of both vertex and even distance transitive graphs. So now, if G is my automorphism group of the graph, so it's a subgroup of the symmetric group on n letters, right, where the letters are my vertices. So I can identify it with a subgroup of the orthogonal group, right? Just view Sn as permutation matrices. And then its action extends to Rn, right? So I can essentially, so for every tau, I can act on the standard basis vector by just permuting it. Yeah, and that gives me an action on Rn. Okay, so then let me fix the notation with which I will be operating. So suppose gamma is a transitive, is a distance transitive graph on n vertices. G.
Can I interrupt you for a minute? Sorry.
Yes.
So in the previous slide, this action G on the coordinates of yes, this action G on the standard basis. So this will never be irreducible, right? Because there is always this subspace that's
true. So
right.
Yes, you're right. However, it can be irreducible on subspaces.
Okay.
Yeah, so that's where I'm going. Yes, you're right. But if you restrict it to subspaces, it can be to certain subspaces, it can be irreducible. Yeah. Okay, good.
And this theorem about tight frames from a group action, this is only for irreducibles, right? Irreducible action.
Right. So irreducible.
Right. Okay.
Right.
Okay.
Yeah.
Okay. Thank you. Thank you.
My pleasure. Okay. Yeah. So so gamma is distance transitive graph. G is its automorphism group. A is the adjacency matrix. Now, suppose lambda is an eigenvalue of A, and let me write V sub lambda for the corresponding eigenspace. So then G, so while, as you have remarked, G does not act irreducibly on the full space, it acts irreducibly on the eigenspaces. Okay. So now further, so if F is some non-zero vector in the eigenspace, then GF is an irreducible group frame. So, as I said, there are many, so in fact, there are infinite families in arbitrary dimensions of distance transitive graphs. Well, by arbitrary dimension, I mean on, so the number of vertices is as large as you like it to be. So furthermore, there are infinitely many such graphs with rational eigenvalues. So this becomes a valuable source for our lattice construction. And in fact, we have a result that looks like this. So let gamma be a vertex transitive graph on n vertices, and let G be its automorphism group. A is the adjacency matrix of gamma, and suppose lambda is a rational eigenvalue of multiplicity m. So then V sub lambda is the corresponding m-dimensional eigenspace. So let P sub lambda be, so it's a rational orthogonal projection matrix of Rn onto this eigenspace. So then what I can do is I can take the orthogonal projection of the integer lattice Zn onto the space, and I get some lattice in the eigenspace V sub lambda. Now, so it turns out that, yeah, so up to here, I am only assuming that my graph is vertex transitive. However, if the graph happens to be distance transitive, then the lattice that I got this way is strongly eutactic. Okay. So furthermore, the automorphism group of the lattice contains a factor group of G as its subgroup. So essentially, it's G mod the subgroup that that fixes the eigenspace V sub lambda pointwise. Okay. So I will refer to lattices that we obtain this way as lattices generated by graphs. So I should say that we can only prove that this lattice is strongly eutactic in case the graph is distance transitive. However, all the examples that we've seen, even of just vertex transitive graphs, we always get strongly eutactic lattices. We can't prove that it's always the case, but all the examples we've seen seems to be the case. Okay. So in fact, it's interesting to view our theorem in the light of a very classical theorem of Hadwiger. So something called Hadwiger's principal theorem that says that suppose I have a set S of cardinality n in k-dimensional space, n is greater than k. So then this set is eutactic, right? So eutactic, remember the coefficients are not necessarily the same, the eutaxy coefficients. If and only if it is an orthogonal projection of an orthonormal basis in n-dimensional space onto V. So in other words, eutactic configurations always come as orthogonal projections of orthogonal bases from higher dimensional spaces. Okay. So now, in fact, our construction, so lattices from graphs, is precisely this kind of projection. But the difference is that, so in other words, the set that we get is eutactic by Hadwiger, but it is not necessarily strongly eutactic. So in case the graph is distance transitive, we get a much stronger condition. So in fact, the set of minimal vectors of our lattice turns out to be strongly eutactic, not just eutactic. Okay, good. So just a few words about the basic properties of this construction. So well, if you start with the completely disconnected graph on n vertices, the lattice you get this way is just Zn. Complete graph on n vertices. So I should say that whenever I say this construction produces such and such well-known lattice, I always mean up to similarity. So let me remind you, similarity means that right, two lattices are similar if you can get from one to the other by an orthogonal transformation and a dilation. So for all practical purposes in lattice theory, people always view lattices up to similarity. Okay, so the complete graph, K sub n, generates root lattice, A sub n minus 1, right? So this is the sublattice of Zn, which lies in the hyperplane orthogonal to the vector 1, 1, 1, 1. Okay, so a very famous family of lattices, the root lattices. So further, if gamma is a disjoint union of k copies of the same vertex transitive graph delta with a rational eigenvalue lambda, then lambda is also eigenvalue of gamma, and the lattice I get is just orthogonal direct sum of the copies corresponding to delta. Okay, so these are pretty simple properties. So also another fairly simple property here is so if gamma is a vertex transitive graph and gamma prime is its complement, right, in the complete graph. So then so the lattice that I obtain, so suppose lambda is a rational eigenvalue of gamma, and lambda prime is the corresponding rational eigenvalue of gamma prime, meaning it's minus lambda minus 1, like this. So then I get the same lattice. So essentially, a graph and its complement lead to the same lattices. Okay, so then also it might be interesting to look at what happens with product graphs. So there are three kind of standard commutative product operations defined on graphs. So the first is what is called Cartesian product. So suppose I have two graphs, delta 1, delta 2. So then its Cartesian product is defined like this. So vertices in the Cartesian product are just pairs of vertices, uv, where u comes from delta 1, v comes from delta 2. And two vertices are connected by an edge if and only if either u1 is equal to u2 and v1 and v2 are connected, or v1 is equal to v2 and u1 and u2 are connected. So that's Cartesian product. Another one is so-called direct product. So again, delta 1 cross delta 2. So this is a standard notation. The square here and the cross. This is standard notation in graph theory. Direct product is, again, the vertices are pairs, and then two vertices are connected by an edge if and only if both pairs u1 and u2 and v1 and v2 are connected in their own graphs. Okay, and finally there's the strong product. Again, the vertices in the strong product are pairs of vertices, but now two vertices are connected if and only if u1 and u2 are either equal or connected, and v1 and v2 are either equal or connected. Okay, so then one can ask, well, suppose I take two graphs and I take their product, Cartesian product, direct product, strong product. Well, first of all, one can compute eigenvalues of the product graph from the original graph. So there are these three standard formulas for eigenvalues. So if lambda and mu are eigenvalues of delta 1 and delta 2 respectively, so then for the Cartesian product, you get the corresponding eigenvalue lambda plus mu. For the direct product, lambda times mu. And for strong product, lambda plus 1 times mu plus 1 minus 1. Okay, so I will refer to this product eigenvalue as f of lambda mu. So, and then one can ask, okay, so I took two graphs, say two vertex transitive graphs. I took their product, one of these three products. What I got is again a vertex transitive graph. So can I describe the lattice of the product graph in terms of the original of the lattices of the graphs delta 1 and delta 2? And here's our result about that. So I have I start with two vertex transitive graphs on M1 and M2 vertices. So then the product graph, so by star here, I mean one of the three products. So that's going to be a graph on M1 times M2 vertices. And so for every pair lambda I, mu I of eigenvalues from delta 1 and delta 2, I have an eigenvalue, I call it nu, which is computed as I just showed you, differently in case of three different products. So then I have the lattices generated by delta 1 and delta 2 corresponding to the two eigenvalues, lambda I and mu I. I want to understand how does the lattice corresponding to the product graph look like. Well, it turns out to be the orthogonal projection of the integer lattice z to the power m1 times m2 onto the space spanned by this thing. So this is orthogonal direct sum of tensor products. Now, in case, in case k is equal to 1, so meaning I take just one pair of eigenvalues, then I get the lattice, which is just a tensor product. So in other words, so for just one pair, I just get tensor product of lattices. Now, in general, for multiple pairs, I do not necessarily get this lattice. Instead, so in other words, I may get something in the space spanned by this lattice, which contains this lattice, but is bigger. So that's why, so it is in general orthogonal projection of this integer lattice onto the space spanned by this orthogonal sum. Okay, and as I said, everything is up to similarity. Okay, great. So now let me show you some examples. So these are some famous graphs, so famous graphs produce famous lattices. That's how it seems to work. Okay, so for instance, so here are some simple examples. So cube graph, Q3, so it's a graph of 8 vertices. It has rational eigenvalue 1 of multiplicity 3. So therefore, it produces a 3-dimensional lattice. So this is the lattice it produces is A3 star. It's dual of A3. So remember A3, well, AN in general is the sublattice of Z to the n plus 1, which sits in the hyperplane orthogonal to the O1s vector. So dual of a lattice defined here. So dual of a lattice is the set of all points in Rn so that the scalar product with all the vectors of the lattice are integers. So the family of root lattices AN is so it has some really excellent properties. In particular, all lattices, all the AN root lattices are extremal, so they're perfect and eutactic. In fact, strongly eutactic, and AN star are also very nice. They're not necessarily perfect, but they are eutactic, well, strongly eutactic, in fact. Okay, so some more examples. So there's Hamming graph producing a tensor product. So that's because Hamming graph is actually a product graph. So there are several others. So you see the lattices. So I guess one point I'm trying to make with this table is that you can recover quite a few of lattices, well, of well-known lattices with great properties. So a bunch of these lattices are actually extremal. So for instance, Coxeter lattice is extremal. Well, this Coxeter lattice too. All right, so so there are three specific examples that I want to focus on in a little more detail. Okay, so for this, let me tell you a little bit about the three lattices, E8, E7, and E6, kind of in that order. So first of all, so this the AN and DN lattices, they correspond to root systems. So DN is defined, so it's a sublattice of ZN. This one is a full rank sublattice of ZN. And it consists of all vectors whose coordinates are congruent to 0 mod 2. Okay, so for even n, one can define a set Dn plus, which is Dn union this translated copy of Dn, right? Where I'm translating by the all halves vector. So actually, this turns out to be a lattice also. Now, so here's what happens. As you let n, so you start with even n, say n equal to 2. And so Dn, so you look at the minimal vectors of Dn, and you look at the minimal vectors of this translated copy. And the minimal vectors of the translated copy are actually shorter. Is that true? Yeah, that's true. Than the minimal vectors of Dn. So which means that your overall lattice Dn plus has many, but not super many minimal vectors, just those of the translated copy. But then in dimension 8, magic happens. And so the norm, the minimal norm of Dn and the minimal norm of translated copy align. And so you get a huge bunch of minimal vectors. And that's the lattice E8. So it's E8 is defined as D8 plus. So if you guys have seen some results, right? So for instance, the famous theorem of Marina Vyazovskaya, right, on about E8 being the world champion for packing density in dimension 8, right? So what's so special about E8? It's precisely the fact that, you know, the two copies aligned, and you now have this huge bunch of minimal vectors. Okay. So then there are two sublattices of E8, E7 and E6, defined respectively, like this. And then the duals of these lattices are E7 star and E6 star. E8 is self-dual, meaning that E8 star is actually equal to E8. Now, by the way, I should say that, you see, in this table of examples, I don't have E8. And that's not because I am shy and don't want to show you an example that leads to E8. It's because I don't have an example that leads to E8. And in fact, I wonder if there is an example of a graph that would produce E8. My conjecture is no, but I don't know how to prove that. Okay, but E6 star and E7 star I can get. Okay, so these are these lattices. So let me tell you a little bit about these examples of graphs. Oh, how much more time do I have, if any?
You can take 5 more minutes or so.
Okay, I'll try to be quick. Sorry, thanks. Okay, so here's the Schlafly graph. All the pictures are stolen from Wikipedia. I can't do my own pictures. So it's essentially the complement of the intersection graph of 27 lines on a cubic surface. So this graph has eigenvalue 4 of multiplicity 6, and the lattice it produces is E6 star. Okay. Here's another famous graph, the Gosset graph, 56 vertices. So let me not talk much about how to construct it, but it's a famous graph, and that has an eigenvalue 9 of multiplicity 7. And that leads to the graph E7 star. Okay. Now, so I want to tell you a little bit about just a few words about a certain weird fluke, which we don't really understand. And I do believe it's a fluke rather than a law. But here it is. So take a lattice L, take its set of minimal vectors. So you can form a contact, so the contact polytope of this lattice. So essentially, it's the convex hull of the set of minimal vectors. Okay. So sometimes, so there is this notation diplo polytope. It's this is a made-up term, but it's not made up by me. It's Conway and Sloan. So they came up with this idea of diplo polytope. Diplo means double. So a polytope is called diplo if its vertices are, if it's essentially comprised of two copies of pi and minus pi. You know? So its vertices are two opposites. Okay. Okay, so given my contact polytope or polytope in general, I can talk about its skeleton graph. So the skeleton graph, its vertices are vertices of the polytope, and the edges are the edges connecting those vertices. Okay. So here's the fluke I'm talking about. So let me start with the lattice E6 star. So the contact polytope of E6 star has 54 vertices. Well, that's because that's the set of, that's how many minimal vectors E6 star has. So they're split into 27 plus minus pairs, and this is, so the contact polytope, it's a well-known polytope. It's called Diplo-Schlafly polytope. Its skeleton graph is the Schlafly graph, which has eigenvalue 4 of multiplicity 6, and the corresponding lattice is E6 star. So you see what I'm doing, right? I'm starting with the lattice, I'm taking its contact polytope, I'm taking its skeleton graph, I'm then using our construction of lattices from graphs, and I'm getting the lattice back. Okay. Another example, let's take E7 star. Its contact polytope happens to be the gossip polytope. 56 vertices. So the skeleton is this gossip graph, has eigenvalue 9 of multiplicity 7. I apply our construction, we get E7 star back. One more. Start with A3 star. So the lattice A3 star, its contact polytope is a cube. So this is Diplo simplex. So the skeleton graph is Q3, the cube graph, has eigenvalue 1 of multiplicity 3. You apply our construction, you get A3 star back. So does this kind of thing always work? No, definitely not always. These are the only 3 examples we know of where it works. My strong suspicion is that this kind of duality has something to do with all of these lattices, in some sense, living inside of E8. So I think this is some weird property of E8. But I don't have a good explanation for this. So if anybody has any ideas, I would love to hear it. And otherwise, so here's our paper. If you're interested, it can be, I have it on my webpage for people who are interested. And thank you very much for your attention.
Speaker. Okay, so any questions from the audience?
Can I ask some question, please?
Yes.
Thank you very much. This is very interesting. So could you go back to theorem 5, please?
Just a second. This one.
Yes. So this reminds me something that we look at some point, because it seems like what you're actually saying, if you put like the coefficient CI inside your, take the square root, put them as, you can normalize your vector, right? Like x1 for xn, you can assume that they are unit norm vectors essentially by modifying this coefficient. So if I expand the space, then you have a frame. And what you're actually requiring here is that you can rescale the length of each of the vector to make it a tight frame.
Correct.
And this notion, there is a connection between this and what you were calling like this polytope. This can happen exactly when the ellipsoid of minimum volume of the two polytope that you obtain here is exactly the unit sphere. And this is related to the result of Fritz-John.
Oh, the Jones polytope.
Exactly.
Oh, sorry, the Jones ellipsoid.
Exactly. And so I feel like this might be a way to actually look at what you were saying about the lattice E8, because it seemed to me the question is, you take this vector, they're not tight frame, but you can sort of scale them to become a tight frame. You can convert this question into sort of looking for the minimal ellipsoid of that sort of inscribed in your polytope. And if that happened to be the unit sphere, then you know exactly when that happened.
Ah.
I mean, there is a series of papers that I co-author with Gita Kutinyok, and we call this thing like a scalable frame. So a frame is scalable exactly when it satisfies the condition that you have here. And we gave like a complete characterization of when this happened. And it turned out that the John ellipsoid are exactly going to need to be exactly the unit ball in order for this to happen.
I see. May I ask you to send me your paper? I'd love to look at that.
I'll do that. Okay. But the
Thank
connection with the lattice, the last one, is quite fascinating. I'm actually curious to sort of.
Yeah, so am I. Yeah.
Thank you very much.
Further questions?
I would have a question. So yeah, thanks for the interesting talk. So you explained how to go from a graph, so distance transitive graph, to these lattices you're looking for, these strongly eutectic ones. And is there maybe a way aside from this special contact polytope to go from the lattice back to the graphs? So can you get all distance transitive graphs, for example, by looking at these lattices?
I see. So you're now asking for the way back. So
yeah, right.
I start with a lot of, okay, so let's say we start with the set of minimal vectors of some lattice. So let's take some very nice lattice. So nice properties in the set of minimal vectors. Then, so what do? So how do I define a graph? You want this minimal vectors to be vertices. So two vertices. Okay. So what you can do is you can take a you can take the automorphism graph of the lattice, and then, for instance, you could say. So I need to think about how to define the edges, right? Because so it's got to be something about the action of the automorphism group, or maybe some subgroup of the automorphism group. There are various conditions on lattices in terms of properties of the action of the automorphism group on the minimal vectors. But from the top of my head, I'm not sure how to define a graph, but I'm sure it could be possible, but I haven't thought of
Okay,
that.
Thanks.
Yeah. Thank you.
So I have a question.
Yes.
So you you say that the motivation to do this is to consider the packing densities, right?
I mean, this is kind of it's a famous problem, so
Okay.
it's always good to state
Right.
as a motivational problem. But the lattices we produce are just strongly eutactic, so I'm not at all suggesting that they're necessarily extremal.
Right. So for extremal, so this Voroniz's theorem says it has to be perfect and eutactic.
Correct.
Right. And so did you consider when these lattices produced from distance transitive graphs are perfect? Well,
so the examples, let me go to my table of examples. Many of the examples are extremals, and many other examples we produced are extremal, but not all. So for one thing, extremal lattices are irreducible, meaning that and also extremal lattices. No, extremal lattices can be tensor products, but they're irreducible. So my guess is that you don't want to look at product graphs or graphs that can be decomposed as products. So for instance, like Hammond graphs, probably not the most interesting cases. So it's probably more interesting to look at irreducible graphs. But no, I don't have an understanding of when you get extremal lattices. And in fact, I don't know what property of the graph would result in the perfection of the corresponding lattice. I don't know that.
And do you have, can you say something about the packing density of the lattice that you produce?
Well, I mean, for these examples, the packing density is known. It has been computed, but you're asking, can I? Okay, so I produce. So somehow, can I express the packing density in terms of the original data of the graph?
Right.
I think so, because so I think the minimal norm. Yeah, I think so. I think it's possible. We haven't done that, but I think it's possible.
Right. Okay. So my question is basically, can you produce like an asymptotically good sequence of lattices?
Yeah.
By considering an asymptotically good family of graphs.
Right.
Distance transitive graph. Right.
So, not that I know of. So, there is a different but related construction. So, not there's another construction of lattices that I studied with some other people, which is actually vaguely related to this, although different, so-called lattices from abelian groups. And there we do get an asymptotically good family. But here, no, I don't think so. At least not that I know of.
Okay, interesting. Well, thanks for the talk. It was very interesting.
No, thank you.
Any further questions?
I had a question. It was about that duality slide near the end. So you were saying that the method that it was happening there only worked, you only found that it worked for those three cases. What exactly breaks down with when you're starting out with other lattices?
Well, so let me try to remember with other examples that we tried. This was a couple of years ago. I'm trying to remember what broke down. Well, so right. I mean, in particular, your skeleton graph may not necessarily have a rational eigenvalue of correct multiplicity.
Okay.
So that's the first thing that can break this. So in other words, here, it lands right in the right spot, right? I get a rational eigenvalue of that correct multiplicity, which is kind of a miracle. In general, I don't think there's any reason to expect that this would happen.
Okay.
Yeah.
Okay, thanks.
Oh, my pleasure.
I have one question.
Yes.
Is there an example of a tight frame that generates a strongly eutactic lattice, which is not an irreducible group frame? I think you said E8 may be such an example. Do you have other examples?
Yeah. So take just a second. Take any rational ETF, like the equiangular tight frame. That's gonna give you a lattice. In fact, a very nice lattice. But it's not. No, it's not necessarily a group frame. No.
Okay. Any further questions from the audience? All right. Let's thank the speaker again.